Hello, myself Professor Harish Bangale. I welcome you on the YouTube channel of Department of First Year Engineering. Myself from Electrical Engineering. I welcome all of you on behalf of SND College of Engineering and Research Center, EULA. So we are discussing the basic electrical engineering subject. In that, we are discussing the alternating current, the fundamentals of alternating current. In that, we discussed how to find analytically and graphically the average value, RMS values, different terminology related to alternating quantities that we already studied. Now, let us discuss with the vector compass and the vectors and the phase shift and phase difference. Right? So, let us begin with that. So, here the vector compass is shown. Now, all of you knows vector has both magnitude and direction. So, here it is the first quadrant, the second quadrant, third and fourth quadrant. This is a 0-degree line. It is 90 degree. It is 180 degree. It is 270 degree. If we rotate vector from in anti-clockwise direction, so from 0 to 90 degree, 180 degree, to again to do 360 degree, then this is corresponds to the positive half cycle. This is corresponds to from 0 to 80. The alternating quantity will be from 0 to pi degree, that is 180 degree, it constitutes the positive half cycle. And for negative half cycle, from 180 degree to again to 360 degree, it constitutes the negative half cycle corresponding. And the one complete rotation of this vector constitutes the one complete cycle of an alternating quantity. Okay, so whenever it is negative, we rotate the vector negative, so it comes in minus 90 degree, okay, minus 180 degree, minus 270 degree, and here again 0 degree. So like this, the vector compass is there. Now we will discuss the magnitude and the angle. So every vector has certain magnitude and angle. Okay, now here the first vector is shown, its length is 7, means its length is 7, means magnitude is 7, and the angle is 0 degree, means angle is 0 degree, means this vector lies on this x-axis itself, which makes the angle of 0 degree with this x-axis. Okay, so it coincides on this 0 degree axis only. Okay, and its magnitude is 7, so it is be indicated like this. So here the magnitude is 7 and angle is 0 degree. Here another vector is shown whose length is 10, the magnitude is 10, but angle is 180 degree. So it is obviously on vector compass, we can locate it here on 180 degree axis. Okay, in opposite direction to that of 0 degree. This direction is here towards the right side. Okay, so that is the difference. Means angle affects, or angle means it is direction. Then this is a vertical length is 5 and angle is 90 degree, means it is on a positive y-axis. Similarly, here length is 4 and it is a negative y-axis because this angle is 270 degree or it is minus 90 degree. Okay, now this is a tilted one, inclined. It makes an angle of 45 degree with the positive x-axis. So here you can locate here in first quadrant, making an angle of 45 degree with this 0 degree axis or positive x-axis. So similarly, here is another vector is there. It is again inclined and it's making an angle of 302.01 degrees, that is minus 57.99 degree. Okay, so it is in fourth quadrant. Okay, and its length is 9.43. So in this way, a vector has both magnitude and direction. Depending on the direction, that vectors are located in different quadrant of a vector compass. Now this vector representation we will see. Now this is a sinusoidal wave having a magnitude v1. Magnitude v1 means its peak value is v1. So instantaneous value is v1. Okay, so it can be represented like this v1. Okay, because it's making an angle of 0 degree with the positive x-axis. Okay, 0 degree axis coincide with the 0 degree axis. Means this vector can be represented like this. Means this sine wave or the equation in terms of equation, if we write it down, then equation for this sine wave will be v is equal to vm sine of theta, and here theta is equal to 0 degree, and that's why theta is 0 degree means it is making an angle of 0 degree with the x-axis. That's why its vector can be represented like this. And this vector representation is nothing but, we can say this vector as a phasor representation of the sinusoidal voltage. So this is nothing but my phasor, and the phasor is nothing but, it is a vector, and that vector is nothing but phasor in for this alternating voltage waveform. Now here different waveforms are shown, and for that each waveform the corresponding vector representation, vector is nothing but my phasor representation, right? So that phasor representation is shown. So here its magnitude you locate on its magnitude, its maximum magnitude, compare the magnitude of all these three. It is small, it is greater than first one, and it is again greater than second one. Okay, so amplitude increases. So here the corresponding length of this vector is also increases. Okay, so it is length is small, here length is bigger, and again the length is bigger than the second one. Okay, and the direction, if you consider the direction for all these is same, because they are all making an angle of 0 degree, only their amplitude is different for the voltages. That's why their length or amplitude is different, but the direction is same. So these are again the different waveforms shown. Now here what you observe that two waveforms are there, waveform A and waveform B. So here in between the two waveforms there is the phase shift of 90 degree. There is a phase shift of 90 degree. So A is first and B is second, means I can say that A is ahead of B, means I can say A is leading B, or in another word I can say the zero value and the maximum value of waveform A appear